So let's now see if we can take some of the lessons we've learned in this analysis and apply them to the problem at hand, which is really to look at our pure states of L squared operator. Now, one of the first things we did was when we looked at what the pure state equation looks like. So in this case, my eigenvalues would be these, or pure state values would be these L squareds. L squared y equals just a number, L squared y. Once again, it's going to be useful to carry out some kind of a dimensional analysis here. And so I would like to label this L squared quantity as h bar squared to give it its units times some appropriate dimensionless label that we can put here. Now, to determine what goes in there, it helps a little bit to think about the properties of what these pure state values must be. And one way to do that is to, again, look at the definition of the L squared operator. So let's imagine I calculate the expectation of my L squared operator in some pure state of L, in particular this state here. Now, on the one hand, that should sound pretty trivial. If it's pure with respect to L squared and the pure value is L squared, well, the average of that would just be L squared. The advantage of this, though, is we can break this operator down into its component pieces. It's an Lx squared plus an Ly squared plus an Lz squared. And, of course, I can decompose this into its various pieces, right? This is Lx squared plus the average of Ly squared plus the average of Lz squared. And now we begin to see the advantage of writing it out this way, because there's a few things I can observe. The first is that, well, the average of the square of any observable, every time I observe the observable is real, and then I square it, I'm going to get a non-negative number. So this has to always be at least 0, and likewise for these other components. So right away, I can conclude two different things. The first thing is that L squared itself, these pure state values, must all be at least 0. That tells me then that when I write L squared as something times h bar squared, I should write something here that I can always remember is a positive number. Well, one way to cover all possible positive numbers is to pick the number and to write it down as the square of something else, where that something else has to be a real number, of course, otherwise I may not get a positive number when I square it. And if I want to cover all possible positive values, I can cover them actually by taking all positive real values for lambda and squaring them to represent my L squared. So that's the first thing I'm going to do. I'm going to code my L squared using this particular form. That's the first thing I can conclude. But I can go do a little better than that, actually. If I'm also looking at states that are pure simultaneously now with respect to L squared and with respect to Lz. This is why we went through the argument to show that we can in general expect that we will find a complete set of pure states that are pure with respect to both of these observables. I can use the fact that if I'm looking at one of these pure values, pure states of Lz also, which is my plan, I know the expectation of Lz squared, because every time I measure Lz, I get mh bar. So this quantity here is also happens to be equal to mh bar would be each individual measurement. I'm squaring those, m squared h bar squared. And of course, when I average all those same values together, I just get m squared h bar squared. So the second thing I conclude is not only that L squared is at least 0, which is what allowed me to write L squared as lambda squared h bar squared, but I can conclude that L squared is also at least as big as m squared h bar squared. Now, when I combine those two facts, that I'm calling L squared by the name lambda squared h bar squared, and the fact that this has to be at least as big as m squared h bar squared, that gives me a very nice relation, where my code name then for my angular momentum squared in dimensionless units, this lambda, right, which we've always chosen to be a positive value, that's the way we had decided on labeling these things, or at least a non-negative value, must always exceed the square root of m squared, which is the absolute value of m. That's another key fact that we can make use of later on. Now, intuitively, I think this is kind of easy to see, right? Lambda and m just measure angular momentum in angular momentum units. Lambda measures the total angular momentum, which must exceed at least the angular momentum or the magnitude of the angular momentum along the z direction. So this is sort of a natural, intuitive idea. We've proved it rigorously, and the remaining piece is just to remember we're doing everything always in units of h-bars.